Welcome everybody to the July meeting of the Mornington Peninsula Astronomical Society, and I'll start with a few things that have occurred in the last month. Showing up there at the top left, we mentioned Stephen Slater and his visit to the Society to give us a talk a little bit earlier. He was actually the main NASA consultant for the movie Fly Me to the Moon, which is currently showing in Hoyt's cinemas, and it's Scarlett Johansson and I think Channing Tatum or some name like that, starring in that one, and it's all about a faking of the moon landing as Plan B in case it didn't actually go to plan. So I haven't actually seen it yet, but it's a rom-com and could be quite interesting. Down below here, below that one, showing the dishes there in, or the antenna there in Western Australia. This is Leo Labs' facility for tracking low Earth orbit satellites. They detected the breakup of a Russian satellite back in late June, and it broke into 250 odd pieces due to a small explosion, was what the comment was about it. They're not sure whether it's the propellant just went bang and blew it to pieces, or whether it was something a bit more than that, or whether it was just an unregistered piece of space junk. So a bit of space junk that they didn't actually know was up there actually collided into it. Well, those 250 pieces were flying all over the place and endangering an area of about 500 kilometres, I think it was, radius. And so on the 26th of June, the International Space Station went into safe haven mode, where basically they tell everyone to hop in the escape pods just in case we need to bring you back down to Earth very, very quickly. And indeed that's what they did. And they were in that mode for about an hour until all the pieces went flying by, and nothing actually hit the International Space Station in that particular case. Then we move on to the top right, shown on the screen there, and in about 2 weeks' time, on the 1st of August, LEGO is releasing their Apollo 17 lunar rover. For those who feel keen for that one, there's only 1,913 pieces, so that should keep you going for at least a day or so. And so I don't think it's open for pre-order at the moment in Australia, but I think that might only be in the US. And the funny little thing in the top right-hand side is a representation of the Lego moon rock that they brought back from Apollo 17, if you're wondering what that funny little thing is there next to the rover. And lastly, down the right-hand side, and you'll hear a bit about this tonight, Guido covers it in Sky for the Month, and I'll show a couple of charts as well. What you're seeing is down here, if you look at where the cursor is a plot here of brightness along the y-axis and the year along the x-axis. As you see, it's around about the years of where World War II was, so 1945. And what you see is the brightness of a star known as T Corona Borealis, because it's a variable star in the constellation called Corona Borealis, the Northern Crown. And as you see the brightness of it, if I get down to point there, it stays fairly constant, then it has a bit of a dip, and then several months later, all of a sudden, it shoots up in brightness. And ordinarily down at a magnitude 10, you're going to need binoculars to see it, or possibly even a small telescope, maybe 2.5-inch diameter telescope. But when it goes into outburst, it goes up to about magnitude 3, magnitude 2, so you'd have absolutely no trouble seeing that with your eye as well. And why that's quite exciting is because that pre-dipping there of the brightness has been observed in recent months, and they were predicting around about August, September time, we may be going into an outburst of that particular star again. And I'll just show you a star chart there from Stellarium. This is a naked eye view. And you'll notice down here there's due north, and this is the view at the moment outside at 8:30 tonight, so in about 10 minutes time. And you'll see Corona Borealis is there inside the yellow rectangle, and you see it looks like a half circle. Because it's a Northern Hemisphere constellation, you need to turn it upside down, then it looks like a crown. Right, it goes up like that. And the actual star to watch for is the one in the centre of the crosshair circle there that is pointing. and it's given a trivial name as the Blaze star, but its proper name is T Corona Borealis. Now, that's the naked eye view. If you focus on the yellow rectangle and zoom in on it, this is what you'll get in a pair of binoculars. And so here's the Corona Borealis, and there the T1, the T Corona Borealis, is that star there. And this particular chart is a variable star observers chart. It identifies several stars on the chart and how bright they are. So, for example, that one there that's got a 9.4 next to it means it's magnitude 9.4. So you can then work out by comparison as to how bright T is at any one time if you wish to actually submit observations of that to keep an eye on it. And as I say, that one is suitable for binoculars, and maybe a 2 to 3 inch diameter telescope would also work as well. All right, so tonight, agenda-wise, we're obviously going through the welcome at the moment. Then we'll look at events past in the coming month. We'll go into Astromofo with Chris, then Sky for the Month by Guido, which is pre-recorded. Then we'll look at Cataclysmic Variables, of which T Corona Borealis is one. A talk given by an amateur astronomer in the US, Walt Cooney, who did a great talk all about them. He's a member of the board of the AAVSO, which is the American Association of Variable Star Observers, and also the Houston Astronomical Society. So this was the talk he presented to the Houston Astronomical Society a couple of years ago. And then we'll close shortly after that. Now, before I go into the recent events, I'd like to welcome new members since our meeting. We've had really two new members since then. One is Sharon Mason and family, and also Stephanie, if I've pronounced that correctly. So I see Stephanie here. I don't know if Sharon is here, but welcome to the Society. And I know we've met Stephanie already as well. So welcome, and feel free to get up at any time and have a cup of tea or a cup of coffee. I'll also make one important announcement now that there's a deadline by the end of the month if you wish to order any merchandise, such as Society clothing with logos and that on it. So you've got until the end of the month, otherwise the booking's closed, because we have to put them in as a batch, and it usually is only done about once a year. So if there's interest in any of that, we'll come and see any of us, and we'll point you where to go for that. So recent events, we had the big school night at Coringal Primary School. First time we've done that school before. And we were expecting 300, but as it turned out, 250 turned up on the night. That was all of school, years 1 to 6, and they got 95% cloud, but nevertheless that 5% enabled them to at least have a good look at the moon at the end of the evening. So that actually went really well, and they were really pleased with it. And I can just imagine what it would have been like if it had been 0% cloud. They would have been super pleased. 21st of June, Phil had the Echo House visitors here at the Briars. They didn't get a talk, just a quick look at the facilities and through telescopes. And for them, they got 0% cloud, so they had a great evening. Day after was the Working Bee here at the Briars, and the following Tuesday we had a committee meeting via Zoom where they talked about the donated sky shed, which you can see in the back there being disassembled in Rosebud. And you can see the size of it there relative to Greg Walton on the right and Mark Hillen on the left. And of course, you can't see Phil Peters because he's the one holding the camera. And doing the usual dad's holiday family photography thing where you never get to see him because they're the one holding the camera usually. Public night on the 5th of July, Trevor had 0% cloud as well for that one, so that went very well. And we had the cosmology group up here at the Briars on the Saturday. Coming soon, this Friday we got the Wolseley Car Club, and if you're wondering what Wolseley cars look like, you can see some of them in the picture there. Coming up to the Briars. Fortunately, by the looks of it, they've all got hard tops on, so if it's raining, they're not going to fill with water on Friday night when they come. Manfred will be giving the talk for that one. We were anticipating probably 30, maybe if the weather's a bit rough, fewer will actually turn up, or maybe they won't bring their precious Wolsleys along. They might come in a somewhat lesser car, but you never know. This Saturday, the working bee at the Briars is still on at 4 o'clock, as far as I know. Committee meeting will be next Wednesday, so we'll move back to Wednesdays from now on. And any member of the Society is welcome to dial into those committee meetings and listen, and we'll post that to the E-Scorpius email group, the link to that each month. 26th of July, we've got another Scouts night here at the Briars. We only got 3 people booked at this stage, so it could be a very quiet and intimate event with lots of questions being asked for a very small number of people, but we'll still go ahead and have that night, even if it ends up only being 3. Public night is booked out on the 2nd of August, where Trevor will be giving a talk. Middle of August, we've got National Science Week, and we do an additional public stargazing night on the Friday of National Science Week, and that one is also booked out. Cosmology Discovery Group, the next one is on the 17th of August, which is a Saturday here at the Briars. And then the next meeting here is on the 21st of August. And then a couple of days later, we got the Latrobe Valley Astronomical Society coming up to visit us here on a Saturday, where we'll throw a barbecue for them.
Sorry?
Yep.
I was just looking at the 16th of August. Is that another public night?
It is, yeah, it's a Friday.
What's the idea behind that? Because we only used to have all of January, we had 5 with the school holiday. What's the idea?
This one is actually inside National Science Week, so it's on the Friday. It's inside National Science Week, which is like a once a year sort of celebration. So we've always done it on the Friday in August as well, that falls in National Science Week. And with that, I will throw over to Chris.
Welcome everybody to AstroMofo number 16, our monthly astrophotography challenge for members. Okay, the last challenge was Cosmic Zoo, or animal related. So basically things that we see in the sky that are related to animals or things like that. And the first image that I've got here was sent in by Kelly Clitheroe, and it pretty much shows the entire zoo. We've got the Milky Way stretching across the middle of the screen there. And also the Milky Way is also the indigenous astronomy figure, which known as the Great Emu. So the constellation has the emu's head right up the top there, which is right in the Coalsack Nebula over the Southern Cross. Its neck stretching down, its body through there, through the middle of the Milky Way, and its legs stretching out through the back there. So that one was sent in by Kelly. Kelly's an Astronomical Society of Geelong member, but she's also a member of MPAS as well. Okay, people who completed this challenge were myself, Chris Kostokanellis, Greg Walton, Guido Tack, Kelly Clitheroe, Nick Axaris, and Sylvie Grandit. Not Sophie. And no, KFC. Yeah, this is Sylvie's photo of the running chicken, which is just off the Southern Cross. You've got the brights, so you've got the, whoops, hang on, let's go back. Okay, 20 by 30 second frames with her Red Cat 51, so it's a fairly small telescope, able to get a pretty nice field of view. We've got the Pearl cluster up the top there, and the bright star there is Lambda Centauri as well, which is one of the hoofs or one of the feet of the Centaur. Some people refer to this one as Caldwell 100, but C100 or Caldwell 100 actually refers to the star cluster in the middle of the chicken. The chicken itself is IC2944. Next we've got a couple of photos sent in by Nick Axaris. The first one we might have seen before. It's the Hand of God cometary globule 4. But Nick's done some more work on this and collected some more time and reprocessed it, and is resent it for this challenge as a giant space worm. So cometary globules are pillars of dust where you have star formation. This one looks like it's a giant worm about to gobble up that little galaxy over there. So this is in the constellation of Puppis, just west of the Carina and Vela constellations. The other one is the famous Eagle Nebula, and I think, is it there? Yep. So we've got one of the famous Hubble images is the Pillars of Creation, which is right in the middle of the Eagle Nebula, and you can see it on the front of the lectern here if you ever come up to have a look. And it's in the constellation of Serpens. So both of these images have been imaged by Nick over multiple nights, multiple seasons, in fact, using different cameras. So you can actually collect your images over multiple nights and keep collecting every season. You get new photos of the same object, add to it to improve your images. And the last one by Nick is the Lobster Nebula, NGC 6357. And we've got a lobster about to devour a koala bear in the middle there. So that's a zoomed in image of the unknowing koala about to be eaten by a giant space lobster. So this is also in the constellation of Scorpius. Yeah, it's an interesting one. Sorry? A lobster eating a koala, yeah. Who would have thunk it? Not the koala, no. Okay, Greg also took a couple of photos as well. These are all taken here at the Briars with the telescopes in the observatory and Greg's DSLR. So all pretty much 30 by 30 second exposures at 3200 or 6400 ISO. We've got the M6, which is the butterfly cluster, an open cluster in Scorpius on the left. And on the right, we have the Bug Nebula, which is a planetary nebula also in Scorpius. Greg also managed the lobster, the tarantula, and the cat's paw. So most of these are actually in the Milky Way. The Tarantula Nebula, however, in Dorado is actually in the Large Magellanic Cloud, which is around about 170,000 odd light years away. So it's quite a distant nebula, but being so distant and so bright gives us an idea that it's actually a massive, massive star-forming region that is extremely active and extremely bright. So these ones were with a 127mm refractor. What else have we got? The Meade, the 350mm Meade, and the other one is also with the refractor. So a couple of different telescopes getting a few different images there by Greg. Next we've got, a couple more from Kelly. We've got quite a few actually from Kelly, so I'll just go through them quickly. We've got the Tarantula, and this one's the Blue Horsehead Nebula. So the Blue Horsehead is actually just off the front claws of Scorpio. It's a really beautiful reflection nebula. It's quite faint though. It's not really visible. The Tarantula you can actually see naked eye from a dark side. It actually is a little blotch in the Large Magellanic Cloud. The Blue Horsehead though, you've got no chance of seeing that naked eye, not even through a telescope. It's really faint, really requires a lot of exposure time to image it, but it's a pretty beautiful nebula. Kelly also got the cat's paw, the running chicken, and the eagle with her telescope. And these ones were captured by a sea star. So those of you who don't know what a sea star is, it's a little gadget, telescope and camera all in one unit. You mount it on a tripod and it's able to align itself, and then it's able to stack images of whatever object you choose. So it'll slew to the object and it'll start stacking automatically the images of the object that you want to point to. It works with plate solving and that sort of technology, and MPAS actually has one. And you usually see Nerida driving it at the public viewing nights and so forth. So we can actually have a play with one at the members' barbecue or whatever other time. So they're a really easy to use, handy gadget that you control from your smartphone, and you're able to get pretty decent, reasonable images of deep sky objects. So we've got the lobster, the Dragon Zavara, which is quite a dramatic nebula, looks like two dragons having a go at each other. The Eagle, the Swan Nebula in Sagittarius, and the Prawn Nebula as well in Scorpius. So these are all, you'll see where these are actually located relative to each other in a little bit, because I've pointed them all out. But okay, this is a new one that I'd never heard of, the Galactic Kiwi, imaged by Kelly Clitheroe. So the giant emu is the Australian constellation in the Milky Way. And can anyone see where the Kiwi is? not I knew someone was going to say that. Not that one. Can you see where it is in the Milky Way? Yeah, right down there. So this isn't an ancient constellation. It's not like a traditional Kiwi Maori constellation or anything. This has only come fashionable in the last couple of decades, where someone took a photo of the Milky Way as it was setting down. They thought they saw a shadow of a giant Kiwi walking across the mountains as the Milky Way was setting. So yeah, it became known as the galactic Kiwi. And one of the ideas is that the Kiwis decided to come up with it as in response to an increase in interest in Australian indigenous astronomy. So this is their answer to our giant emu. But as all things, as all good things New Zealand, I reckon we can pinch it for ourselves and call it the giant echidna or something, the galactic echidna, and make it Australian. And you never know, it might win a Logie or an Oscar or something. Okay, these are my photos. So started off with a running chicken and a couple of different lenses here. So the one on the left is just with a standard camera lens. It's a very cheap standard camera lens, a $50 one that I bought from a second-hand shop. And I mounted it on my Astro camera, and just to have a bit of a play with it and see what sort of fields of view I could get. And this is what I got of the Southern Cross. So we've got the Southern Cross there, and that's where the running chicken is relative to the Southern Cross. And you can see this dark nebula here is the head of the emu. So if you can see that why the chicken is running, it's trying to get away from that giant emu. So the other good thing about using these lenses with the cameras, I've got a filter drawer on my camera. I'm able to put in different filters, light pollution filters as I did for that shot, or dual band filters as Guido's done with a couple of his shots that you'll see, and get some nice shots. One on the left is through the telescope with a dual band L Extreme filter, and that's around about 220 minutes of exposure. Then I've got the cat's paw, the dragons, and the eagle. Really interesting object in here with the dragons. This is called the dragon's egg, or it's known as the dragon's egg. And what it actually is a binary system of two giant stars, one 26 and one around about 30 solar masses, which are circling each other. The idea, main thinking at the moment about that nebula is that it was originally a 3-star system. 2 of the stars merged and became the 30 solar mass star. When they merged, they threw out all of this material, which became the Dragon's Egg Nebula in the bottom there. So they reckon that that nebula there is only around about 7,500 years old. So all of this happening astronomically relatively recently. So it's a really interesting little object. This is through an 80mm telescope. So I think it'd be really interesting to try and image it through one of the larger telescopes that we have here as well. Okay, now on the weekend I was down at Heathcote at ASV's Dark Sky site and got a bit of a play with my camera. New 10mm lens gave me that shot of the giant emu flying across the radio dish there. That's a single shot, and then also the Swan Nebula as well, which is data from last year's South Pacific Star Party of just a UV filter, and then also added some photos with the L Extreme filter as well, the dual band filter, to come up with that. And also, this one is with that same lens as before, the 10mm lens, on my Astro camera. So this is at 20mm focal length, and I've got Scorpio here, so I was trying to get some images of Scorpio, and this is about 29 stacked frames. So we've got the claws of Scorpio there, the body and the heart of Scorpio, Antares there, and its tail swinging around to there. And in that field of view, you can see a lot of the other objects. The Blue Horsehead Nebula is just up there when you have a look at it, relative to the rest of Scorpio. What else we got? Guido. Okay, Guido had a similar setup to what I had, but he used a dual band filter. So he's pulled out a lot more nebulosity in the Milky Way from his photo there. So that's about 55, 60-second frames. These are all tracked on a little tracker or a mount so that you can take the long exposure shots without your stars trailing. And also he's got the Great Emu here as well with the same lens and the same filter, I believe. Okay, here we go. This is where everything pretty much is relative to the Milky Way. So the running chicken is just off to the right there. There's the Southern Cross, there's the emu's head, and there's the running chicken just off screen. CG4, the giant worm, that's way off screen. That would be down, looking down at the ground somewhere. It's on the other side of Carina. The tarantula is sort of down here somewhere on the floor, relative to the Milky Way. The fighting dragons, that patch there. The prawn nebula is in there somewhere. The bug nebula is in there. That's the cat's paw there. The lobster nebula there. The butterfly cluster just off that. And the Swan and Omega nebulas are just off the screen in that area there. So that's where all of this stuff is in the Milky Way relative to, or in the Milky Zoo. Okay, our next challenge is Indigenous astronomy, Australian Indigenous astronomy. So we're looking to get images of the sky from our First Nations culture's perspective, Indigenous objects such as the Great Emu, but there are many, many more of them. One starting point that you could look at is aboriginalastronomy.com.au. It's a website that's got a lot of information on Indigenous constellations that you might be able to image. And also Stellarium. If you go into the star law section of Stellarium, it includes objects from the Kamilaroi and the Burong people as well. So it'll show up. This is actually a screenshot. The back is actually a screenshot from Stellarium, which shows a lot of the different Indigenous constellations. These are great to image with wide field cameras, probably even at maybe 100 or 50 mil focal length or even wider. And you'll be able to get some of these. So it'd be interesting to do a fair bit of research on this. Now I'm running this over 2 months again, and that is to give us a chance to become a bit more familiar with them, with the constellations, and get a bit more information and try and get as many of them as we can. So at the next member meeting, I'll put together a bit of a talk on Indigenous astronomy, or maybe might be able to get somebody to come and do it for us, a bit more knowledgeable than me, and tell us a bit about it, and we'll run this challenge over the next 2 months, which pretty much you don't need a telescope to partake in it. You can have a look at the sky, look at the programs, and try and capture these objects. Submit your photos to either to the socials or to the eScorpius groups, or email them directly to me for inclusion in the summary. I've got a reminder that we're doing a calendar, so if you do have any great shots that you want to submit for inclusion in the MPAS calendar for next year, I think we probably need to get that in by maybe the end of August to get that printed up. So I'll let you know very soon when that needs to be done by to get it printed. And also we've got the astrophotography workshop coming up. So if you are interested in learning more about taking astro images, either with a telescope or with a camera, deep wide field images and that sort of thing, you can book on the website. If you go into the events section of our MPAS website, go through there and you'll be able to get on to book for the astrophotography workshop. And that's me. Any questions? No? Well done everybody who took the images. So yeah, really great work. And keep them coming. You don't have to be an expert to send images in. Really want to see images from people who are maybe just taking their first shots as well. So please submit.
Hello and welcome to Sky for the Month for July and August 2024. Let's start with a view of the inner solar system as seen from above. Venus and Mercury are early evening objects, while Mars is still an early morning object at the moment. Zooming out, we can see that Earth is catching up to Saturn and Neptune because it's faster on its inner solar system orbit. So those two planets are rising a bit earlier now than for the last few months. Now let's look at the night sky on the 1st of August. The sun sets around 5:30 now, around 10 minutes later than last month. And you can see that Venus and Mercury are visible just after sunset in the evening sky. Mercury will actually be very close to Venus and the Moon on the 6th of August, and Venus is now an evening object and will remain there for the rest of the year. So we're fast forwarding to around 10 p.m. now, and you can see Saturn and Neptune rising a couple of hours after sunset in the east there. So Saturn will be a very good viewing target for the next few months because it's heading towards opposition in September, when it will be exactly opposite the Sun as seen from Earth. So very nicely positioned in the sky, and we should get nice views of Saturn with its ring plane almost closed at the moment. We'll have an image of that in one of the later slides. When we look at the brightest stars in the sky at the moment, we still have the Southern Cross very prominently, very high in the sky towards the south, and the two pointer stars next to it. Antares, the heart of the constellation Scorpius, is the red star that's now near the zenith around 10 p.m. And around Scorpius and Sagittarius, we are looking into the core of our Milky Way galaxy. So there's a lot of great objects to observe in that area of the sky. We have globular clusters like M22. We have the Trifid and Lagoon nebulas. We have M6, the butterfly cluster, M7, Ptolemy's cluster, the Eagle Nebula, which is M16, and so on. So lots of very interesting targets, really nicely positioned high up in the sky towards the zenith at reasonable hours now, around 10 p.m. to midnight. So further along the Milky Way, towards the north, we have Altair in the constellation of Aquila, the Eagle. Let's have a quick look at the constellations for the month. So we can see Sagittarius and Scorpius near the zenith, and then we have Virgo and Libra towards the west, and Capricorn and Aquarius towards the east in the sky at the moment. All right, let's head a bit further through the night and towards the early morning. So we can see Saturn and Neptune now crossing the sky, I think transiting somewhere around midnight to 1 a.m. And then just after midnight, we will have the remaining planets rising. So we can see Uranus just rising there in the east now, and then followed by Mars and Jupiter as well. Jupiter rises around 2:30 a.m. and it will be within less than half a degree of Mars on the 15th of August. So that might be a very nice opportunity to capture both of those objects in the sky together. Mars rises around 2:30 a.m. at the moment, and it will be within 5 degrees of the very bright star Aldebaran in early August. So very easy to spot those two together. And finally, for the moon, we have the next full moon on the 21st of July, the next new moon on the 4th of August, and then the August full moon on the 20th of that month. The August full moon will actually be a supermoon, which means that it's a full moon where the moon is also at its closest to the Earth in its orbit. Sunrise is now around 10 minutes earlier than last month at 7:20. Here's a quick overview of the apparent sizes of the planets in the sky at the moment. We can see that Mars is getting a bit bigger now compared to previous months, and Saturn is also getting a bit bigger because we're heading towards opposition. And you can see here how the ring plane is almost closed, so we're almost looking at the ring's edge on at the moment. It will actually open up a little bit over the next few months and then close completely by February, March next year. One other thing I wanted to mention this month is something you may have heard about in the news. So astronomers are expecting a star in the constellation Corona Borealis to go nova anytime between now and maybe 2026. The star is currently too faint to see with the unaided eye, but it will increase in brightness to third or even second magnitude. And that's as bright as the fourth brightest star in the Southern Cross. So it'll be very easily visible with the naked eye. So let's zoom into Corona Borealis. Borealis just means northern. So this constellation is towards the northern horizon as seen from us. So it's up there in the northwest. If we zoom into that part of the sky, we can see it's pretty much directly in the northwest, and it's this half ring shaped constellation. That's the southern crown Corona Borealis. Sorry, the northern crown Corona Borealis. So T Corona Borealis, the star that's expected to go nova, is a very faint star that you can see there in the middle at the moment. It's much fainter than the stars of the actual constellation Corona Borealis. And you need a telescope and kind of good star hopping skills to see it at the moment. But yeah, it will brighten somewhere in the near future to a brightness that's brighter than the actual stars of the Corona Borealis constellation. So let's have a quick look why that's happening and why we know that it's happening. So T Corona Borealis is actually a binary star system, which means there's two stars orbiting each other. One of them is a red giant star and the other one is a white dwarf. And the red giant star is basically losing hydrogen that's falling onto the surface of the white dwarf star. And when that hydrogen on the surface of the white dwarf reaches a critical mass, it basically explodes in a thermonuclear explosion like a hydrogen bomb. And because it's quite predictable how much hydrogen falls onto the surface every month, every year, and so on, it's every 80 years that it reaches this critical mass and then explodes. So this star, this nova, has been observed regularly over the last centuries. And we know that it exploded 80 years ago and it's due for an explosion in the next couple of years. It's not 100% guaranteed that this will happen in the next couple of months, but during the last nova, astronomers observed a dip in the brightness of the star in the months before the nova. And the same thing happened in February, March this year. So that's why some astronomers are expecting this to happen in August or September this year. But it's also possible that we'll have to wait another year or two for this to happen. A quick look at comets in the sky. Unfortunately, nothing very interesting right now. 12P Pons-Brooks, which was a good object over the last half year or so, is now only magnitude 11 to 12 and fading. The other two comets, they are only listed for completeness, but they basically set just after sunset, so not exactly great opportunities to view them at the moment. In terms of meteor showers, we have the Perseids starting around now and being active until late August, but they are not a great shower to observe from the southern hemisphere, so there might be a few meteors very low on the northern horizon. The other two, the Delta Aquarids and Alpha Capricornids, were already mentioned in Sky for the Month last month. So they're still active until around mid-August, with the peaks still to come. So that might be something to look out for. And that's all for this month. As always, my sources were Stellarium, NASA Eyes on the Solar System, and the Astronomy 2024 yearbook.
Now for the main talk, this one will go for over an hour, so if you need to get up and stretch your legs any time, please do so. Don't feel embarrassed, or get up and go outside and help yourself to a cup of coffee and then bring it back in is quite fine as well. This is showing Walt Cooney, a very seasoned variable star observer, and he's going to tell us all about the different types of cataclysmic variables that go boom. And the T Corona Borealis is just one of them. He actually has a master's in chemical engineering from Cornell University, and as I said earlier, he's on the boards of the AAVSO and also the Houston Astronomical Society, which this is taken from one of their meetings.
Tonight's topic is cataclysmic variables, stars that go boom. As I'm sure many of you know, supernovae in particular have been recorded in ancient history. We've known about those for a long time, those new stars that get so bright. This is a Chinese document that's highlighted here where they discuss the new star in 1054 AD that we know now as the Crab Nebula. And then this is a rock carving in India that's been projected against a map of the night sky to show here's their version of Orion and here's their version of Taurus, and there was a supernova that they saw, we believe, back in about 3600 BC. At least that's one interpretation of that stone carving. And then this is something from a book showing the 1604 Kepler supernova, and this is the constellation Ophiuchus. And if you see this star right here that's got an N, a kind of circle, that was the location of Kepler's supernova in 1604. And so here's what we can show you of those supernovae. Can't show you the supernovae now, they have already exploded. But we can still see what's left of them and how that's even changing, believe it or not. So this is the supernova that happened in AD 185. This is the remnant, and it's an infrared picture made with the Spitzer and the WISE space telescopes. This remnant is about 8,000 light years away. It has grown to be about 85 light years across at the moment. And the supernova, our best estimates were that it got up to about magnitude -8, which is bright enough that it was seen in the daytime. And just for comparison's sake, Venus at its brightest is about -4.7, so it was several magnitudes brighter than Venus in the night sky and visible in the daytime. Another one that was recorded is in 1006 AD. This was in Lupus, and 7,000 light years away, 60 light years across at the moment. It got up to magnitude -7, and so it could also be seen in the daytime, and it's quite a beautiful shot of the remnant. And this is actually made across multiple spectra, multiple bandwidths. This is a combination of an X-ray image, let's see, X-ray, visual light, and radio, all three combined into this kind of a false color image to show those different wavelengths. This is the supernova of 1054 that was shown on that Chinese document, and it's now our Crab Nebula, Hubble Space Telescope picture, and 6,500 light years away. It's now about 11 light years across, and it got up to magnitude -6, and so also visible in the daytime. And then we had a run on supernovae for a while. In 1572, there was one in Cassiopeia, and it's called Tycho's supernova. And this is an interesting shot from the Space Telescope. So on the left, this is actually Chandra's X-ray view of the remnant, about 9,000 light years away, 25 light years across. The supernova was about as bright as Venus, give or take, -4. But on the right is a Hubble Space Telescope picture. And so this little star must be this one in the box here. And as we'll talk about in a minute, supernovae are the result of binary stars where one of the stars is a white dwarf, and that white dwarf explodes and completely disintegrates. And the secondary star, the other star in the binary pair, now doesn't have a companion anymore. It's blown out, and we think we figured out which star that is, and it's this one. It's as you notice, it's not in what would be about the center of the remnant. It's free to travel now that it doesn't have its binary there, and possibly the supernova blast wave gave it a push in a direction too. So quite the neat picture, quite the neat finding. And let me see if I can play a video here, and I'm going to take off full screen. So this is a montage of that supernova in X-ray light from the Chandra X-ray telescope. And as you see the year counting up here from 2000 to 2015, and I hope you can see this in this web meeting, the supernova remnant is still growing. We're watching the movie of it there. We had a run on them. You just mentioned this one in 1572. Just a few years later, we had one in Ophiuchus. That was the one I mentioned. We showed it down in the foot of the constellation. And here are 3 different images of the remnant. On the left, an X-ray from Chandra with a close-up. And in the middle is what we see visible light. Not so much to see invisible light, unfortunately. But here's zoomed in a little bit on a portion of that. And then here's infrared with the Spitzer Space Telescope and zoomed in again. So this one is about 20,000 light years away. It's about 10 light years across now. And it only got up to magnitude minus 2.5. And so that's give or take around as bright as Jupiter gets. And you know, this one was quite far away, 20,000 light years. But the other thing that made this one a little fainter was that we're looking back through a dense portion of the Milky Way, and there's a lot of dust between us and where this supernova happened. And so that dims what we see and also reddens what we see. And so it wasn't as bright as some of the others before. And by the way, 1604, that's the last one I've got to talk about right now. And so we're due. We're ready for another one to go off in our galaxy soon. Although that said, our galaxy doesn't have a monopoly on supernovae. Here's one that went off in the Pinwheel Galaxy M101 back in 2011. I imagine at least some of y'all had seen that back in 2011. It got pretty bright, I think, and I don't, okay, yeah, 10th magnitude. And so it was easily in reach of, 6-inch telescope, something like that, no problem. Really smaller telescope than that would have been able to see it. And there are literally dozens of these supernovae discovered every year now. Okay, so the topic is cataclysmic variables. And we've shown pictures of a bunch of supernovae remnants. But there's a whole lot more to cataclysmic variables, a whole lot more kinds of stars that go boom. So we talked about supernovae, we mentioned novae, and some of the other ones that happen or that occur are what are called dwarf novae, recurrent novae, nova-like variables, polars, intermediate polars, Z-cams, and the list goes on for quite a bit beyond that. And so what are these things? Hopefully some of y'all were able to make the August HAS meeting where Bill Pellerin discussed stellar evolution. And so that's the birth and death of individual stars. And what Bill was talking about, like I say, was individual stars. So what happens if stars are in a binary system? And as you may know, most stars in the universe actually are in binary systems, the majority. Our sun is a little bit of an oddball in that it's by itself. And the answer to how they evolve is if these binary stars are widely separated, then they evolve just like two individual single stars. They don't interact much. The two stars evolve independently, grow old, and die as to their course, depending on their mass, as Bill talked about in August. But if the stars are, quote, close, then things change a lot. Now they do affect each other. All right, so we got to talk just a little bit about some of the science behind this. And so the key concept is what's called a Roche lobe. And so if you look at this graphic, you see these two teardrop-looking forms, two teardrop-looking shapes around the two stars in a binary system. And so this shape is kind of like a gravity boundary inside of the surface. any matter really belongs to that star gravitationally. Outside of the surface, it's really impacted by both stars. It's well, a difficult concept to explain, actually. But the critical point for us is there's this thing called the first Lagrangian, and this actually, I think they call it the Lagrange point rather than Lagrangian, but this is where matter is equally tugged on by this star on the left and this star on the right. And so that's pretty critical in how these close binaries eventually interact and evolve. And here's why. So you end up with a situation where one of the stars has grown old, has gone from its normal starhood, like our sun is in right now, and it starts moving towards a red giant phase. And when that happens, it expands, and it expands to fill its Roche lobe. And then matter starts leaking out of that Lagrange point here and moving towards a white dwarf as the second star in the binary. And when the material heads towards this high gravity white dwarf, it actually can't just flow directly in. You know, the material coming off the donor star has some spin to it. And so angular momentum keeps it from just taking a straight path in. Instead, it spirals in to the white dwarf, and we call that an accretion disk. And so to give you a feel for the size of what we're talking about, the typical scale here, the distance between the two stars, is something like the Earth-Moon orbital distance. So that's round about 250,000 miles. And the orbital periods are 1 to 10 hours. And so those things are screaming around each other. You know, the moon and the Earth revolve around each other once a month. And so 1 to 10 hours is just a wee bit faster than that. And so this is the key thing that's happening in cataclysmic variables. So here's an artist's conception of that, a little bit more than just the diagram we saw. And so the white dwarf is down here in the center of the accretion disk. And then here's the donor star and the mass stream coming off of it. And where that mass stream first starts to kind of impact the accretion disk, that's actually called the hot spot. And a bunch of nuclear reaction going on there, and it flickers and changes brightness over time. So that's kind of an artist's rendition of what your average garden variety cataclysmic variable star really looks like. So here's how we get there. You know, I talked about in this cartoon, you see we've got two normal stars that are rotating around each other. In this case, they're fairly close to each other. And as stars grow older, the heavier or more massive star ages more quickly and moves into the giant phase. And so that's in this next frame here. So this is the heavier massive star starts to expand. Eventually it expands so much that it overflows the Roche lobe and starts draining matter down onto the other star. And then rather than an accretion disk, at this point what you get is something they call a common envelope. Basically the star that's growing older and expanding kind of engulfs the entire pair. And that stage only lasts something on the order of, say, 1,000 years, which, as you can imagine, that's less than a blink of an eye in astronomical terms. But the thing that happens is the common envelope is ejected from the binary pair. And that's where we get an awful lot of our spectacularly beautiful planetary nebulae. And the reason why so many of those planetary nebulae aren't just these perfect spheres, perfect rings, perfect circles. They have all this strange spirographic shape to them. And it's because they're actually from ejected material from binary stars. And so that gravity, that rotational inertia that came from that original common envelope and those two stars rotating around each other continues to shape that planetary nebula as it expands from the pair. All right, so once the common envelope is ejected, what we're left with of that big massive star that had expanded is now just a white dwarf. And this is exactly the same thing that's going to happen to our sun. You know, it will, on its lonesome, it will expand, it'll go to a red giant, it'll puff off its outer layers. That'll be a beautiful planetary nebula for somebody else to enjoy. And we'll be left, our sun will be left as a white dwarf. So we have the white dwarf and the original secondary star. Well, the secondary star eventually grows old too. And it expands just like the first one did, and it fills its Roche lobe, and it starts leaking mass over onto the white dwarf. And so if you notice, one thing that's happened here is, although it's one way the cartoon doesn't do this justice, the mass flow has reversed. The first thing that happened was this was the first star, the massive star, was sending all its material over towards the less massive star. Now it's the less massive star that's pushing material over to what's left of the original big one, which is just a white dwarf now. So I think that's kind of interesting. I wish they had drawn this cartoon so you could more easily see, so that they kept the stars on the same side of the graphic each time. But anyhow, so as the material spirals down into the white dwarf, it builds and builds. And at some point, the white dwarf, which typically might be, say, one solar mass, about as much material as the sun, it grows and it grows as the mass leaks from the other star or is pulled from the other star. And finally, the white dwarf reaches what's called the Chandrasekhar limit, which is about 1.4 times the mass of the sun. And at that point, what's called electron degeneracy, which is what was holding that white dwarf from collapsing in on itself, the electron degeneracy is finally overcome. There's just too much mass. Gravity has become too powerful. And the result is the star heats up and maybe starts to shrink a little bit, but you get what's called a carbon flash. And so the large amount of carbon that's in this white dwarf now goes into nuclear fusion, and the star is just plain disintegrated. It is completely wiped out. There's really nothing left to speak of. And over here in this last frame, you see the donor star now swinging off into infinity, free of its original binary pair there. And that's how we get what's called a type 1a supernova. And this is generally what happens across the board in cataclysmic variables. There are some variations, and that gives us different kinds of cataclysmic variables, but this is the crux of it. This is the outline for how they happen. So a few more words about supernovae. So they'll rise in brightness 15 to 20 magnitudes. And as you guys may know too, type 1a supernovae have become relatively famous in the astronomy world, and maybe even slightly outside the astronomy world too, because their brightness, their absolute brightness, is quite constant between different supernovae. And so we have used them as standard candles to tell distances in the universe. And back about 15 years ago, give or take, maybe 20 years ago, two different groups used supernovae explosions to examine the rate of expansion of the universe, and came up with dark matter and dark energy and all of that kind of bizarre stuff. And they got the Nobel Prize. Both groups got the Nobel Prizes for that work. And so these are those standard candles. And so the funny thing about it is there's actually two ways that we get these type 1a supernovae, and that's kind of the puzzle that's still going on to this day. The first one, we just kind of walked you through that cartoon of you get a white dwarf and a cataclysmic variable, gains mass, the white dwarf passes the Chandrasekhar limit and explodes, and the fact that that happens at a defined 1.4 solar masses is why it's kind of a standard candle. You know, it's the same amount of mass that goes kablooey each time. So it's the same 1,000 sticks of dynamite each time, although maybe it's just a little bit more powerful than that. And let me show you, let's see, this is not going to work right. No, I'm going to go here. Okay, so here is an animation out on YouTube of a supernova, type 1a supernova explosion in progress. And so this is the donor star that has expanded, filled its Roche lobe. You see the matter streaming out of the donor star, coming down into the accretion disk, then spiraling down into the white dwarf here at the center. And so let's play this. Oops. Okay, that one was going to go off twice there. Let's see. Okay, so that was quite the neat animation. I'm not sure that music was physically recorded at a supernova, but I don't know. It could have been. So anyhow, I said though that that's not the only way to get a supernova, a type 1a supernova either. Apparently, a lot of supernovas happen because instead of a white dwarf and an aging star in a binary pair, you actually have a binary pair of white dwarfs that they merge and pass the Chandrasekhar limit in that merged system and then explode. And the thing that's quite odd about this though is we talked about 1.4 solar masses being such a magic number. That's why you get a standard candle, because that's how much material explodes. Well, if you've got binary white dwarfs that merge, and one of those white dwarfs is about 1 solar mass, and the other one's about 1.1 solar mass, and they merge, and now you've got an explosion of 2.1 solar masses. And so how is that now still a standard candle? And the answer to that is good question. And that's an area of active research right now. As a matter of fact, one of the really interesting things that they have seen not too long ago was in 2003, they saw a supernova, type 1a supernova, that was apparently much brighter than it was supposed to be. And they have gone back and tried to work out the theory. And this one seems pretty clearly to have been a merger of white dwarfs that combined to substantially more than the 1.4 solar masses. And as a matter of fact, this was in 2003. There was a popular song in that era, and so they actually named that the Champagne Supernova. And there have been several Champagne supernovas that have gone off since then. And they're intensely studied right now. This is still something we just really don't understand. And it's so critically important because these are our standard candles. This is one of the ways that we get to dark matter and dark energy. So we really need to understand them. Okay, well, there are exceptions to the double star cataclysmic variables that I've talked about, and those are type 1b, type 1c, and type 2 supernovae, and these are different. These are from a single very massive star that grows old very quickly because it's so massive, and then the core collapse. It goes through core collapse as it progresses up through the different levels of fusion. And we've seen one of these pretty recently that was actually visible naked eye, although you had to live in the southern hemisphere, or at least farther south than we are. This was supernova 1987A in the Large Magellanic Cloud. And here to the right is a 1994 Hubble Space Telescope picture of the remnant of this type 2 supernova. And you can see various rings here. This was material that had been thrown out from the star previous to it going supernova. And then as the radiation now expands violently from where that supernova happened, it's lighting up those rings of material as it passes through them. So, all right, so let's go on to another kind of cataclysmic variable, classical novae, or just novae. And so these aren't quite as energetic. They don't get quite so bright. They rise in brightness something like 7 to 15 magnitudes, which is still a lot. And so in this variation of that binary star theme that we talked about, we've got hydrogen from the donor star that moves through the accretion disk and then builds a layer of hydrogen right at the white dwarf. And when enough of that hydrogen has built up, that hydrogen layer, and not the underlying white dwarf per se, but the hydrogen layer now goes nuclear and is ejected. And so the white dwarf and the companion star both remain behind, but part of the white dwarf actually does get ejected too in this energetic explosion. And so here's another question that comes up. All right, well, I thought the way that we got a supernova was mass slowly filtering down from the donor star until the white dwarf got above 1.4 solar masses, and then it all goes kablooey. But the white dwarf loses mass when a nova happens. And so if you get novae first, because the material builds up on near the white dwarf, how do you ever get beyond up to 1.4 solar masses to have the supernova? And what I can say to you is, good question. And so again, it's something that we don't really understand, and there's a lot of research trying to figure that out. Here on the right is a graphic on a picture showing Nova Cygni, 1975. I don't know if any of y'all happen to be around and happen to notice this one. I was around for it, but I don't remember seeing it or looking for it even. It actually happened in north of Deneb, and so this would be the North American Nebula right over here. And so it was pretty close to the North American Nebula, 1975. And we'll actually mention a few more words about Nova Cygni 1975 in a bit. All right, well, so what other kinds of cataclysmic variables are there? Well, there's dwarf novae. We talked about supernovae, we talked about regular classical novae, and then there's dwarf novae. So these are even smaller. These rise in brightness about 2 to 6 magnitudes. Their outburst, their explosion is different. Now the hydrogen builds down into that accretion disk, but the accretion disk is an active system, and the accretion disk itself can build up matter and ignite. And so it's not the hydrogen layer that's down near the white dwarf which gives you a nova. This is before you ever get to the white dwarf. So that's called that gives you a smaller explosion. And dwarf novae can go off quite frequently. Some of them go off every few days. Some of them go off weeks, months, years apart. And there's all kinds of other strange things that happen with dwarf novae. There's something called a super outburst. So an outburst that gets even brighter, and that's when the nuclear reactions that are happening in the accretion disk go off, and you get nuclear energy where the matter is physically falling into the white dwarf. So you get a second bump there. And so these super outbursts are now even brighter than the initial outburst. And there's more funny things. There's something called a super hump, and that's on top of a super outburst. You get additional brightenings that show up in a periodic nature, and these are caused by deformations, kind of warping of that accretion disk. And another thing to mention is flickering. So this isn't twinkling like we see when we look at a star in our atmosphere. This is actually flickering of the light of this star system. And so it's a real short time scale, seconds, minutes, very quickly. And it's the matter, it's two things really, at least that's what we think now. It's the nuclear energy being released where the matter is falling into the white dwarf down at the bottom of the accretion disk. And it's also some flickering at the hot spot that I showed you out on the edge of the accretion disk where that matter is falling down onto the accretion disk. The theory until not too long ago was that the flickering was all happening at the hot spot. It was just sitting there basically sizzling with nuclear explosions as that material came from the donor star. And we figured out that that's not it, or at least that's not most of it. And the way we know is because sometimes these binary systems are edge on to us, and we can figure out from the light curve where the hot spot is in the light curve. And when the hot spot is eclipsed, we still see flickering. So clearly the hot spot at least isn't the only thing doing it. And we can further tell because we can see in the light curve where the white dwarf is and where the matter is falling into the white dwarf. So again, just from looking at eclipses and that geometry and those light curves, we can figure out that the flickering is coming from both, with most of it, we believe, coming right at the white dwarf itself. So anyhow, lots of stuff here. There's even more things, but I wanted to give you some flavor of all these interesting and strange things that happen in these binary systems, and we can physically see these in our light measurements. And speaking of which, here's some light measurements. These are AAVSO curves, light curves, contributed by amateurs to the American Association of Variable Star Observers. And you can get out on the web and pull these anytime you like, pull these curves. SS Cygni is a dwarf nova. It's one of the prototypical dwarf novae. And the x-axis here is days, and Julian days actually. And so here's 400, here's 500, here's 600. So in about 100 days, this star goes faint and bright and faint and bright 3 or 4 times in 100 days. I think nominally they call it a 22-day period. although you'll notice it doesn't do that like clockwork. There's a fair bit of variation. Here it kind of stalled out a little bit fainter, although not as faint as it could be. And something else to mention on these graphs is these measurements are made by amateurs, and the black circles are made by amateurs with modest telescopes and their eyeball. Those are visual variable star magnitude estimates, and we've got folks active in our club who do that. I mentioned Brian Kudnick in particular as an incredibly active AAVSO member who has contributed tremendous numbers of these magnitude estimates of variable stars. But in the green are amateur measurements with telescopes with CCD cameras, or DSLRs for that matter. And one thing that's important to notice is, the CCDs and the visual observers really agree pretty closely, and the visual observers are doing tremendous work. You could certainly argue that the CCD can be very, very accurate, but it's amazing how good the human eye can be at doing this as well. Okay, so let's go down. SU Ursa Majoris is another dwarf nova, and I wanted to show you this one because this is one that has the super outbursts I talked about. And so here are the regular up and downs where it's going through normal outbursts. And then every so often it has a super outburst. And if you remember, that's when you get the addition, not just of the accretion disk lighting up, but you also get the matter falling into the white dwarf lighting up brightly. Let's go on. There's another one. We talked about novae. Well, novae don't necessarily go off just once. Recurrent novae are a thing too. There are 10 of them that we know of so far in our galaxy, and we think there's a whole lot more than that, but we've only been watching for 100, 200 years, something like that. And so these are the only ones that we know of so far. This is the list, and this shows when they have erupted, the years that we saw them go off. And I'll point out two of them in particular that are kind of interesting. Here's one, T-Pix. So this one would go off pretty regularly. So here's 12 years, 18 years later, 24 years later, 23 years later, and then nothing for a long time. There was a long gap. And so right in this time frame, about 25 years, maybe 30, 35 years after 1967, that's when astronomers started writing papers about why this star apparently would never go nova again. And then they had to throw those papers away because it went off in 2011. So, uncooperative star for sure. And I'll mention another one, that's U Scorpii. And so this one has gone off many times. And an LSU astronomy professor, Brad Schaefer, has spent a lot of time working on this one. And he put out a plea for help to the AAVSO, asking folks to watch out for this one going off. This was in 2019 he did that because his calculations said it should go off any time now, and we just need to keep an eye out. Well, so several folks, a lot of folks actually answered the call, and it didn't go off, and it didn't go off, and it still hasn't gone off. But we think it did go off. We think it went off in 2016 or 2017, but Scorpius is along the ecliptic. And so we think it probably went off in about November when the sun was sitting right between us and it. And so there was no way we could have seen it. And so we just missed it. And I'll talk a little bit that more later. I've actually done some of the work, me and several other folks in the club, to find out what's going on with that star. All right, Z-Cams. That's a strange name. So the very first one discovered of this type is Z camelopardalis. And so they're now all called ZCAMs for short. And these are regular dwarf novae that do their regular outbursts. But then at some point, they're on their way down and they get stuck. And they sit there and kind of sizzle around at the same magnitude for weeks or months. And then they get started again until they get stuck again and sizzle around at the same magnitude for an extended period of time. And this is a recent light curve. Right now, it's still stuck. And so this is another area of research. Why in the world does something that goes off regularly kind of get caught in the middle? All right, this is another strange one. So nova-like variables. So these are non-eruptive cataclysmic variables. These are cataclysmic variables that don't have cataclysms. So how did we ever even discover them? How do we ever even decide that they're truly cataclysmic variables? Well, we see that because the spectroscopy shows us something is going on. They resemble or they act just like cataclysmic variables spectroscopically, even if we don't see them go off. And so we think what's going on with these is there's a lot of matter that's being pulled down from that donor star and sucked into the accretion disk. And so basically the accretion disk is always an outburst. And that's why we see these as never outbursting, because they're always outbursting. And here's an AAVSO graph, but I kind of cheated on this one. So this is magnitude. It normally sits around magnitude 12.9, about magnitude 13 here. But then it's got these things where it drops almost a full magnitude down to about 13.8. And so this is one of those cataclysmic variable stars I was talking about that's line of sight edge on to us. And so this is an eclipse. This is the white dwarf and the accretion disk being hidden by that donor star. And so one of the things you can figure out from that is the donor star must be about this bright, because that's all we're seeing. Normally the white dwarf and the accretion disk far outshine the donor star, so we don't get to see much of it. But now they're hidden. Now we can look at it directly and see what's going on with it. More strangeness. These are polars. Now you've got the case where the white dwarf has a spectacular magnetic field. The Earth's magnetic field is about 0.5 Gauss. The sun at its surface magnetic field is about 1 Gauss, not that much. These white dwarfs have magnetic fields on the order of 10 to 80 million Gauss. And that magnetic field is so strong that you can't actually form an accretion disk. If you look over here to this graphic, here's the donor star. Here's the material leaking towards the white dwarf. And at some point, before you ever get to form an accretion disk, this super powerful magnetic field grabs a hold of that matter and sucks it in on the magnetic poles of the white dwarf. And so these are called polars. And by the way, too, polar, it's not because it pulls the matter in to the pole. It's because one of the ways we can tell this is a polar is because the light coming from this system is polarized. And that's an effect of being pulled into this magnetic field here. So that's where they get their names. But here's the prototypical polar. And it does have outbursts. In this case, it's going about 2 magnitudes from normal brightness up to full brightness. But they keep getting stranger. So this is an intermediate polar. So now we have a white dwarf with a super powerful magnetic field, but not quite as powerful as the last one. the magnetic field here is 1 to 10 million Gauss. And so you get a pretty cool thing. Now you've got the donor star, the material being pulled from it, comes down. It does form an accretion disk that spirals around the white dwarf, but eventually the white dwarf's magnetic field is strong enough to grab a hold of the matter in the accretion disk and pull it up and over and down in the magnetic poles of the white dwarf. And so that's why it's called an intermediate polar, is it's kind of intermediate magnetism, and its accretion disk is a donut. It sweeps clean this inner portion of the accretion disk. And so here's the most well-known intermediate polar. And again, I cheated. This one is edge on to us. And so we're seeing the eclipses where the white dwarf is going behind the donor star. Okay, so where are we going now? How do amateurs get involved? What's important with all this? And actually, why don't I skip down to this bullet? Why do we even care? It's interesting, sure, fascinating to see these stars that go explode and why that, trying to figure out why they're doing that. But there is more to it than that. It turns out these are just really great laboratories to understand how accretion disks work in astronomy. Because as you saw, a lot of these phenomena and cataclysmic variables happen on timescales of hours, days, weeks, months, years. While a lot of accretion disk activity in astronomy is much longer timescales. For instance, black hole accretion disks, planetary formation is an accretion disk phenomena that takes place over very long timescales. And so as we investigate and try to understand how accretion disks function in cataclysmic variables, it lends understanding to a lot of other important accretion disk physics out there in the universe. And so some of the things that we're trying to understand specifically up to the higher bullet is how do we really get to that type 1a supernova? I talked about how there's some real uncertainties there. And this one's pretty interesting too. So in reality, are dwarf novae, nova-like variables, are they really all the same thing, just at different snapshots, different times in their evolution? And we don't know the answer to that, although we think the answer is probably yes. Although it's going to be a really complicated answer with a lot more than just some simple progression, I'm sure. Are all novae recurrent? We talked about there's 10 recurrent novae that we know about now. Well, we haven't been looking that long. And there's a lot of good theory that says that really all novae are recurrent. Now, they may not go off again for another 1,000 years or another 10,000 years, but they're not just a single time happening. More things, and I didn't really get into this stuff, but just to mention a few things, odd stuff that goes on there, things called negative superhumps. There's period bouncing. There's a period gap, I told you, where the typical orbital periods of the white dwarf and the donor star are 1 to 10 hours. And that's true, but between 2 and 3 hours, there are almost none. So there's something strange going on there, and we've actually got some theories why that is. And I also mentioned flickering. You know, it hasn't been that long ago we finally figured out that flickering isn't happening where we think it was. It's not at the hot spot. It's mostly down at the white dwarf itself. Amateur research. That was one of the things I wanted to be sure and mention here is, so what are we as amateurs, what can we do to contribute? There's a hugely active group of people in amateur astronomy doing work in this, both visual and CCD. I mentioned Brian Kudnick in our local group who's done visual work. I'm sure there are others, and I'm sorry for not mentioning your names. There are several folks doing CCD. cataclysmic variable work for the American Association of Variable Star Observers. And so that's an organization that collects data from amateurs, makes that data available to the professional astronomers, and professional astronomers have used that data as a tremendous resource to learn a lot of things, write a lot of papers over the years. Some of the advantages are we get multi-year and multi-decade light curves. We've got light curves for stars going back before 1900. And so you can really see what's happening with some kind of longevity, as opposed to the professional normally getting 2 nights on the telescope next year. Another thing amateurs are doing is we're the sentinels for these outbursts. So when the recurrent novae go boom again, novae like USCO, T Corona Borealis, T Pix, those, it's the amateurs watching for those. Now pros watch too, but amateurs are often the ones who really catch them first. And that's historically been very much the case. And we're also watching for other outbursts. There's a really interesting one that happened this spring where there's a black hole binary. It's now called V3720 Ophiuchus. And it flared this spring and got really bright. And it's had a couple of flare-ups since then. And professional astronomers are scratching their heads, and the amateurs are helping provide the data so that they can try to figure out what's going on. Another important bit, and I've been involved with this a little bit, it's pretty neat to be able to say that you're supporting the Hubble Space Telescope. And that's a little grandiose, but there is a little bit of truth to it. The Hubble Space Telescope and major observatories do cataclysmic variable research all the time, but they get short sessions. They get a night, they get 2 nights, maybe if they're really lucky, they get a week at a major observatory, or 2 hours on the Hubble Space Telescope. And that gives them a great snapshot, but the amateur work over longer time periods allows them to put that work in perspective, see what else that star system had been doing. And actually, we're helping protect the Hubble Space Telescope. And what I mean by that is there's an instrument on the Hubble Space Telescope called the Cosmic Origin Spectrograph, the COS. And it's a spectrograph that's sensitive to ultraviolet light. And so it's very critical instrument to a lot of what Hubble has done. And it's used a lot for cataclysmic variable research. The unfortunate thing is it has a brightness limit. If the object it's observing is too bright, it'll literally damage the instrument. And it would be great not to damage the instruments on the Hubble Space Telescope. And so generally, astronomers working on cataclysmic variables with Hubble Space Telescope don't want to image when an outburst is going on. They don't want to see it explode. They want to see it at quiescence. And if it explodes during a run or just before a run, you're liable to damage that instrument. And so through the AAVSO, the professionals request that the amateurs monitor the particular targets, post their data, and usually within about 24 hours, the professional astronomers have to give the Hubble Space Telescope Institute a go, no-go decision on that observation. And it's kind of neat. What they actually do is what's fed up into the telescope menu a week or 2 beforehand is an observation of the wrong field. And it's not until they get this go signal from the pros looking at the amateur data a day before that they will upload the true target to take the place of that dummy target that was just a safe target. And just this past spring, as a matter of fact, the Hubble Space Telescope was going to observe a cataclysmic variable, and amateurs were able to say, stop. Not too long before they were supposed to point Hubble towards it, it did go into outburst. And so they canceled the observation. They rescheduled it actually, and I think the observation just happened about a month or 6 weeks ago, and amateurs were again looking. This time it did not go off. This time they did have a successful observation. There's another really prominent way that amateurs are contributing in cataclysmic variable research, and that's what's called the Center for Backyard Astrophysics. And it's run by a professor of astronomy at Columbia University up in New York, Dr. Joe Patterson. And he was wise enough to realize that while the pros only get these short time periods on these large telescopes, a lot of what happens, to understand, you really need to see it over longer time scales, and you even need to see it across a 24-hour period. And so by having a global group of amateurs who collaborate with him, we will watch the particular targets and put light curves together that get around this limit of only seeing it for 5 hours every 24 hours. We can actually watch it to some extent all day for weeks or months. And so this has been going on since 1991. That's when he first started it. Telescopes that participate range from 8-inch to 29-inch apertures. So, and there's only one 29-inch. Most of them are way closer to the 8-inch. 12-inch is 12-inch is probably about the average, I would think. And something else, this has been going on since 1991. And so the CBA now has multi-year, multi-decade coverages of CVs. And so we're able to get to changes that happen over those time frames. And so let me show you one down here without going too deep into this. But this is ES SETI. And this is what's called an O-C diagram. It's basically a way you can graph, show on a graph whether an orbit is slowing down or speeding up. And in this case, because what they say is the teacup filling or is the teacup draining? Is the parabola going up or down? In this case, the teacup is filling. And so that tells us that the orbital period is actually getting longer. And on the face of it, that's a little strange, because normally stars in pairs spiral closer to each other over time. They don't grow farther apart over time. So some interesting physics going on with that, and this work is over the 16-year period to see this effect. Something else all this data can do is we can see past the flickering. Flickering is a neat phenomenon. We don't truly understand it, but it's also a pain, because our light curves have all this what seems like noise. When someone first looks at a variable star, a cataclysmic variable star light curve, they say, boy, was your telescope out of focus? What was wrong? And in fact, it's the flickering that just makes the curves noisy. But you get lots of people working on the same star, and you combine all of that, you can average out the flickering, and you can get an amazing light curve like this one, HP Libra. And so this is its orbital light curve. And look at the amplitude. Magnitude 13.698 to magnitude 13.703. 5 1,000ths of a magnitude. And nobody's individual telescope did this. But when you put lots of telescopes together and you have the advantage of statistics, you could do some pretty amazing things. So lots of papers have been published out of this. I'm sure it's more than 100 for sure over the years, and it's still a very active group. And so I help with both AAVSO and the Center for Backyard Astrophysics. Here's just a quick few light curves to look at. This first one is of HP Libra. Okay, I cheated again. This is even another kind of cataclysmic variable star that I didn't list, I didn't talk about. This one is 2 white dwarfs. They call this a helium binary. The accretion disk, instead of hydrogen being pulled from the donor star, is helium being pulled from the other star. And so that's its light curve. You see just a pretty small amplitude and lots of up, down going on with this one. V1080 for Hercules. We don't know if this is a nova-like or an intermediate polar, trying to figure that out. VZ6, sextants, we think this is an intermediate polar as well, but work still to be done. And I'll mention another group doing this. Bill Flanagan, Bill Pellerin, and I support a telescope out near Medina in the Hill Country, and we have used that telescope to do cataclysmic variable work. And so here's a light curve. This is U Scorpii. This is the cataclysmic variable recurrent nova that I mentioned that we thought maybe went off in 2016 or 2017, and we'd already missed it. And so this is a part of the eclipse. This is another one where it's edge on towards us, so we can actually see an eclipse. And by timing the bottom of these eclipses, we can figure out whether it has already gone off or not. And the answer from the data so far is that yes, like I said, probably 2016 or 2017. And our continued work, we should be able to figure out from this analysis whether it actually went off in November of 2016 or November of 2017. We don't have enough data to say for sure yet. Here's another light curve. This is that Nova Cygni 1975 that I mentioned. This is the one that went off near the North American Nebula. And so here's its light curve bouncing around, doing strange things. And when you put this together with many more light curves from many folks, you can start to figure out what's going on. And then the last one to mention, V392 Persei. We talked about our cataclysmic variables, all these kinds of cataclysmic variables, just snapshots of the same kind of system doing different things at different times. And here's some pretty good evidence for that. V392 Persei was a dwarf nova that we'd known about for some time. And 2018, the thing went nova. So there you go. At least we've got one example, and actually there's potentially a second example, but here's one example of a dwarf nova that at some point went nova. And we mentioned that novae potentially happen all the time too, so maybe that connects dwarf novae, and recurrent novae all together. So anyhow, more to figure out, more to learn. Thank goodness we got the professional astronomers to do the detailed analysis on that, to tell you the truth. Okay, that's my presentation. Thank you very much for listening. I hope this was interesting for you, and I'd love to answer any questions if I can.
Hey, Walt, thank you very much. That's a fascinating talk, and I think one of those areas where you kind of really highlights the fact that astronomy is still one of those sciences where amateurs in many regards are still leading the way, right? Kind of the tip of the spear for a lot of the work that the professionals are doing. So thank you.
Yeah, you know, the professionals are limited with those big telescopes on the mountains. They only get those little snapshots, and the amateurs can do things that the professionals really just can't do now.
Right. You mentioned very early on in the presentation about a binary pair, the typical type 1A, where you have a star go to red giant and the white dwarf is nearby, and that they'd be apart, but similar to their separation would be similar to the Earth-Moon distance.
Right.
But
right.
When I hear, oh, our sun's going to go red giant, and it's going to become larger than the orbit of Mercury, Venus, Earth, or maybe even larger, which is way more than 240,000 miles. And so I was surprised to hear such a small distance for the size of a red giant.
Yeah, really the key bit there is the size of the red giant. And what I mean by that, what's the actual mass of the red giant? Because if the red giant is a solar mass, a star with only 0.05 solar masses, then that red giant isn't so giant.
Right.
And so that's the key bit there, is usually this second companion is a dwarf star. And
Right.
I didn't mention that. And then of course it's a red giant, but with the caveat that it's got this whole Roche lobe problem, so that it doesn't keep growing and keep growing. The matter starts filtering off of it. And so the gianthood in that sense has a boundary to it.
So it has the characteristics of a red giant, but not the mass and the diameter of other really big red giants.
Yeah, they're generally smaller than our sun, and a lot of the mass that it would have grown, or a lot of the size it would have grown to, has been lost just because that matter instead gets pulled down into the white dwarf.
It's been stolen, right? Okay,
Right.
great. Thank you.
Right. You're welcome.
Thank you.
All right. Said, how close would a supernova have to be to Earth to be dangerous?
Oh gosh, I don't know. Betelgeuse is something like 500 light years away, and I have heard different ideas on that from different astronomers. Some say that that's far enough and we're okay, and some say, oh no, we're in trouble if Betelgeuse goes. So I'll throw myself at the mercy of the fact the pros don't necessarily know either.
Yeah, and I think there's evidence to say that perhaps some of the mass extinction events that we've had here on Earth may be related to supernova explosions as well, right?
Yeah, well, and if you want to throw that open to other folks who know about that subject, who maybe can shed a little more light on it than I can.
Yes, I have technically two questions. And the first one is about the colors of the supernovae. If they are true colors, I mean, the myriad of colors are true, because I have heard that they retouched the photographs. So I don't know if it's true or not. You see those?
Yeah, okay. No, I think I know what you're talking about. We'll see here. It's very true that a lot of the beautiful pictures that you see in astronomy aren't really exactly what they look like. For instance, some of those supernova remnant pictures I showed with the beautiful colors. Well, those were fake colors. Some of them had X-ray, radio, and visible light all combined into the picture, and so as part of producing that quote unquote picture, they'll assign, say, blue to X-ray and green to visual light and red to radio, and you get the beautiful colors, and it's helpful to see that because you can visualize it in all those wavelengths. But of course, in fact, we can't really see the object like that. So maybe that's what you're getting at.
I have another question. What makes recurrent the supernovae or novae? What makes them to burst or outburst again? I mean, they burst, they lose matter, energy, and they come back to normal, and then what happens?
Well, still active research. It's a good question, and I think the answer is that if you remember, the material works its way through the accretion disk. The hydrogen then builds up as a layer in a boundary layer above the white dwarf, because it can't easily drop into the white dwarf. It's still got angular momentum that it's got to deal with. And so it kind of builds up into a traffic jam right there at that boundary layer until it goes off. Goes nova. We talked about it actually takes a little bit of the mass of the white dwarf with it, but then it goes back to normal, and the donor star continues to lose mass, which continues to drop down in the accretion disk, which can once again build up, have a traffic jam at the boundary layer of the white dwarf, and go nova again. So that's the reason, is there's a continuing supply of material coming off the donor star.
Excellent.
Are there variable stars that don't have companions?
Oh yeah, and thanks for mentioning that, Bram. In fact, this is just one subgroup of the massive number of massive number of kinds of variable stars out there. You know, there are Miras, which are individual stars that go supergiant, and then they pulse and they change color and they change brightness. And there are Lyres, which pulse, individual stars pulse, change color, change brightness. There are Cepheid variables that do something similar, Delta Scutis, gosh. There's a long list of other kinds of variables, and I probably should have mentioned that to give people that perspective. This is just the one subgroup that happens to be interesting because these are very irregular, and they go boom. They give off a lot of energy when they go off.
Now, it feels plausible that you have in the binary where the donor star is accreting material, or the dwarf is accreting material from the disk onto its surface, that you have the fusion there. But this idea of fusion in the accretion disk itself seems quite odd. After all, we're using really high-powered lasers on lithium hydride pellets trying to create fusion in our labs, and we're having a lot of difficulty with it. What's going on in the accretion disk that retains, or actually maybe converts, the gravitational energy into thermal energy in combination with sufficient density to cause fusion?
Yeah, fantastic question. The subject of many research papers and PhD theses over the years, and I can give you an answer at some level. I don't know enough about it to give the hugely detailed answer, but the bottom line is the accretion disk is normally fairly transparent. By transparent, I mean light from the accretion disk can pass through the accretion disk and out into space without too much difficulty. And so the accretion disk can hold a reasonable temperature. But at some point, the accretion disk in some small area that then expands will turn opaque. And there are a number of mechanisms at play. There is gravitational radiation, there's magnetic braking, there's all kinds of things, just to throw out some of the fancy terms. But the bottom line is a portion of the accretion disk will heat up extremely and then go opaque. And when it goes opaque, now the radiation from the accretion disk is more or less trapped, and so it continues to heat up, and eventually it heats up to the point where it does go nuclear, and there are also density waves in the accretion disk. You know, we really didn't talk about, but the accretion disk is a spectacularly complex system. I've read through, paged through some of the books on the accretion disk physics, and just spectacularly complex things going on there. And so I can't answer you directly other than to say that that's kind of the mechanism. Is there's kind of a low state where the accretion disk is mostly transparent and cooler, and the high state, the outburst state, where the accretion disk is hot and opaque and goes off. So I hope that kind of answers.
Yeah, that's a partial answer.
Okay.
Thank you.
Sure.
So it's not really increasing the density to anything that we would experience here on Earth. But
I don't think so.
The temperatures are going bizarre in certain portions of the disk.
I think that's right. There are most definitely density fluctuations, but it's I don't think it ever gets to the kind of densities that you might be talking about otherwise. Although, to tell you the truth, it's something I need to spend a little time looking at and be sure I know the answer to that. That's a good question.
All right, thank you.
I have one other question. I know most of these systems were double star systems. Are there any things more exotic than that? Triple star, quadruple star systems? Any novae coming out of those types of systems, or?
Not that I know of, but I'm sure that's the wrong answer.
It just popped into my head. I was thinking, well, I wonder if there's,
Yeah, I really haven't read about that. I've kind of wondered the same thing. You've got to believe that there is such a thing.
Sure.
I will say, though, that when you get to things like triple star systems, multiple star systems, usually the physics of the gravity there means that the three aren't all close to each other. Those kinds of systems wouldn't be stable.
Right.
So triple star system, I think, might be two close ones and then the third one quite a distance away.
Okay, excellent. All right. Well, hey, Walt, thank you so much. I appreciate your presentation. It was a fantastic presentation. I think for many of you, I hope you'll do what I do, is get on the aavso.org website after this and do a little more research to figure out how we can contribute as amateurs to this. So thank you again, Walt. I do appreciate it.
Taking advantage of the total lunar eclipse of January 2019, astronomers, using NASA's Hubble Space Telescope, have detected ozone in Earth's atmosphere. In this observation, Hubble did not look at Earth directly. Instead, astronomers used the Moon as a mirror to reflect sunlight that passed through Earth's atmosphere. This method serves as a proxy for how they will observe planets around other stars in search for worlds similar to our own. Though numerous ground-based observations of this kind have been done previously, this is the first time ultraviolet light passing through Earth's atmosphere was observed from space. The measurements from this experiment detected the strong spectral fingerprint of ozone. On Earth, photosynthesis over billions of years is responsible for our planet's high oxygen levels and thick ozone layer. That's one reason why scientists think ozone or oxygen could be a sign of life on another planet. But finding ozone on distant worlds isn't an easy task. Ultraviolet observations like this can best be conducted from space telescopes above the limiting effects of looking through Earth's skies, because ozone blocks most ultraviolet light from beyond the atmosphere. One of NASA's major goals is to identify habitable and inhabited planets. But how would we know whether a distant planet has ozone or not? The atmospheres of some extrasolar planets can be probed if that distant world passes across the face of its parent star, called a transit. During a transit, starlight filters through the backlit exoplanet's atmosphere. Chemicals in the atmosphere leave their telltale signature by filtering out certain colors of starlight. Astronomers have used Hubble to observe the atmospheres of several gas giant planets that transit their stars. But terrestrial planets are much smaller objects and their atmosphere thinner, like the skin on an apple. Therefore, teasing out these signatures is much more difficult. To prepare for future studies with larger telescopes, astronomers used Hubble to conduct experiments on a much closer and only known inhabited terrestrial planet, Earth. Our planet's perfect alignment with the Sun and Moon during a total lunar eclipse mimics the geometry of a transiting terrestrial planet with its star. But the observations were also challenging because the Moon is very bright and its surface is not a perfect reflector because it is modeled with bright and dark areas. The Moon is also so close to Earth that it appears to move very quickly in the sky, making it harder for Hubble to stay pointed at the same location. However, in spite of the challenges, the experiment was an incredible success, and Hubble is supporting the ongoing quest to find planets that are similar to our own and perhaps, one day, find signs of life on other worlds.
Finish off with the lunar retreat, which shows you a simulation of where the Moon is in the sky today, moving backwards to when it was formed in time, because the Moon is receding from the Earth at about just under 4 centimetres per year based on the laser ranging that has been done. And And primarily the reason why it's receding is because the Earth is rotating, so it gives the Moon a bit of a tug due to the gravitation caused by the oceans, and over time that means it slowly spirals away. So this goes for about 1 minute. And that's a big moon in the sky. And with that, I'll call a close to the July meeting, and we'll see anyone who turns up at the August meeting. Thank you.